I just want to welcome everyone and thank you for attending today. I am George Hamilton from the U.S. Army. I'm going to talk about the Next Generation Combat Vehicle Electrical Power Architecture development for which my team is leading here for the U.S. Army. So I came out of the Stryker program office, as you heard mentioned, and I worked their electrical power system for a while, and I kind of want to create the need as to why TARDEC is developing power architectures. In 2001, and just using the Stryker vehicle as a point of reference, when the Stryker was fielded, it used or had a 280 amp alternator on it. As vehicles were continued to be developed, the next set of vehicles were planned on having a 400 amp alternator in 2004, and then in 2009 I was part of an effort to move to a 570 amp alternator, and that's due to adding lots of loads for the Operation Iraqi Freedom, such as the jammers, the shot detection, the additional radios, the GPS systems. And that started to see this creep of how power was growing. Right before I left the Stryker office in 2010, they were working a modernization program which changed into an engineering change proposal. For that program, as of this year, they're looking to incorporate a 910 amp 28 volt alternator. And then my program that I'm currently working on has a 45 kilowatt or something greater than 1,500 amps, a 28 volt requirement. So the loads on military vehicles are continuing to grow, and so they have this strong desire to go to more electric systems, and these are just for the 28 volt type loads. Currently today, the vehicles, especially if you look at MRAP and Stryker, Bradley, they're all underpowered now for an electrical standpoint. Every program has efforts underway to increase their alternator size to account for this additional electrical load. One of the issues the Army itself has had when it was developing JLTV and both the ground combat vehicle, the Army paid each individual OEM for unique power architecture development when it was purchasing those vehicles. So there was no commonality across those vehicles aside from they would all eventually produce 28 volts. And now all those vehicles did have a high voltage DC system on them. And so here's kind of what we're trying to do. So we don't want to keep paying vendors for unique proprietary systems. We want to be able to reuse our electrical power investments across all of our vehicles. And so the Army is hoping, providing that my team is successful, to leverage this work to pay for power architecture development hopefully one last time. And then we can continue to apply that to all the additional vehicles that are developed once my effort has completed. Concurrently, we're also doing some investments into power management to end up saving fuel on our combat missions, and I'll kind of talk a little bit more about that later. But we believe that we can achieve 10% fuel savings independently of going to a high voltage architecture. And so one of the things that if we're successful, we believe it'll reduce logistics burden, allow us to apply hardware commonly across multiple platforms versus having to have unique power systems in stock for every single platform. Right now, we have Paladin, which is also a 600 volt system, and so if we had that and if the GCV was continuing onward, they would be different systems, and we'd have to stock completely unique DC-DC converters, high voltage power distribution, generator controllers, and all those kinds of things. So hopefully this will allow us to go to a more common set of equipment available. So here's some facts, some things from my work when I was in Stryker. In 2004, we did a silent watch test, which meant we were going to do engine off operation, and we were trying to see how much energy storage we needed on the vehicle to meet the requirements. So one of the things we know, on a combat mission, vehicles are idling 50 hours of the 72 hours of that mission. That's due to a lot of the time is prep, mission rehearsal, and staging prior to executing that mission. So only for about a 24-hour window is the vehicle actually moving, and it's typically at creep speed and then it'll kind of go to a full drive cycle. And so what we've observed is during those situations when the vehicle's not moving, that although the electrical load people are asking for is upwards of 25 kilowatts or so, that we only see about an average usage of about 2 kilowatts on a lot of the vehicles that are fielded today. And on those same vehicles, we have 280 to 570 amp alternators, which is sufficient for where we're at during creep. But what we've learned is that if we use at least the batteries that are available today, the absorbent glass mat, we have Hawker batteries, what we call them, on our vehicles, that I can run that vehicle on battery only for about 3 hours and then recharge to 90% state of charge within 1 hour. So kind of in rough calculations, we believe, if we move to an advanced battery chemistry, and we're looking at using lithium ion in our architecture, that I could run engine off about 75% of the time when that vehicle would be parked and idling while it's preparing for that combat mission. And so I believe, if we can save 75% of the fuel during that time, that'll lead to about a 10% or more system fuel savings across the entire 72-hour combat mission. And so that's kind of one thing that we're looking at from the power management side, is to add anti-idling. Now, this has been common in automotive for a long time, but the military has not done any efforts to date where this has really been a focus. And so I have a couple different efforts going on where we're working on that. So kind of why high voltage? So I came from the Stryker office where we were trying to do Stryker modernization. Our goal in that program was a 30-kilowatt system, and I kind of walked through how we came at this decision we needed high voltage. At the time, we noticed that the largest alternator anyone was able to produce for us was about 910 amps at their traditional alternator size. It was about 25.5 kilowatts. And when we went to package this alternator, it was a little bit of a challenge, and it really didn't meet our full growth requirement, which was to get up to 30 kilowatts. We also noticed that if we would move to a higher voltage, we could save on size and weight the government pays quite a premium for by reducing that by going to high voltage. And then we started looking across multiple platforms. Bradley, Stryker, and GCV all had power requirements 30 kilowatts or greater. And so we kind of saw that maybe there could be some commonality if we went to a common high voltage standard. And so, so I believe new approaches are required to do an electrical power systems, the kind of the way the military has been doing it. But admittedly, the military is very adverse to trying new things, and they're concerned about safety mainly with these high voltage systems. So in Stryker modernization, back 2010, a decision was made that that system was going to be a 600-volt architecture before that program was shelved in 2011 to save costs and kind of reduce scope to an ECP effort. So it is my belief, and several here around me at TARDAC, that for any vehicle that needs 26 kilowatts or more across all engine operating speeds, that they're going to have to use a high voltage system. And so we think that they'll end up using our 600-volt system once we finish development on that. Now, why 600 volts? I wish there was a nice technical reason as to why we chose the number 600 for what we're targeting, but I'll kind of walk you through all the trades that at least I was involved with and how we arrived at that. So when I was on Stryker, we did an ISG trade study which showed we were trying to achieve a certain power density. And what we learned on that is that the current rating on each phase of the ISG, we needed to have at least 400 volts AC phase-to-phase to achieve the power rating at 120 kilowatts and the size density we're looking for. And so they said, well, we should have at least a 400-volt DC system or greater. And at the same time, there was the Future Combat Systems program was just kind of winding down, and they had a 600-volt or 610-volt architecture. And we kind of looked at, hey, the Europeans had chosen 750-volt systems, and then Boeing had this new plus-minus 270 or 540-volt architecture. And at the end of the day, we just went with 600, mostly because it was most compatible with the previous FCS investment that had happened, and we wanted to give U.S. suppliers, which had worked with that, the largest chance of competing, because at the time they had not dealt with the 750 volt that was solely European. So that's really why we chose 600 volts. Now, the reason we couldn't do 610 is because the actual voltage specification for FCS was proprietary to one of the vendors, and so we had to do something slightly different in order to have our own voltage standard. And so in working with that on Stryker, we learned a few things. One, when we go to high voltage, we need to have liquid cooling to cool the power electronics. And so we were targeting an ADC liquid cooling loop, and that caused us to have to install quite a large radiator to dissipate. I think at the time it was roughly 25 kilowatts of heat load we had to dissipate, along with the extra coolant pumps and those types of things. And so the radiator ended up being a bit of a challenge, along with the coolant pump, to get that integrated. Additionally, the size of the silicon-based power electronics at the temperatures we had to package in, the inside of the engine compartment on the Stryker was 121°C. And so to get electronics that would work in that kind of ambient, even with the ADC coolant, they were quite large. And as it turned out, as we got close to PDR, or the preliminary design review on that platform, that we were going to struggle to package all of the power electronics in the engine area where we wanted to. And so when that program ended, we didn't necessarily have a solution to that. And so that's kind of where I got involved with silicon carbide. One of the things that we've learned with silicon carbide is that we can reduce the size, weight, and power, which basically efficiency we can increase, of these devices. We can also operate them at a much higher temperature, and so we're targeting 100 to 105°C, which allows us to reduce our radiator size required for the same system by about 60%, and so that makes these systems a lot more feasible for integration. We've also noticed that the power density is going upwards of 50% or more on these systems. Right now, I have an effort with General Electric to deliver to me a 15 kilowatt DC to DC converter, and it's going to be half the size of the 10 kilowatt DC-DC converter that we're going to field on Paladin. And so that's some of the reason that I'm really excited about using silicon carbide within the platform. Now, silicon carbide itself is a bit more efficient than silicon, so there actually is less heat generated for the same amount of performance. And what we've noticed is for every kilowatt of electric loss that we need to dissipate, it adds to about 5.3 horsepower of engine cooling power required out the radiator. So also, like I said before, having additional cooling capacity within the system will allow easier integration and also increase reliability. We've noticed that we can have a loss of some of the cooling components with silicon carbide and continue to operate, albeit for a minimal amount of time, but we are able to have no-flow coolant requirements and be able to meet our needs within the silicon carbide devices that we're looking to get. So some of the requirements of the architecture, at least that we're trying to develop to kind of constrain what we're trying to achieve. So we took the requirements from Stryker, Abrams, Bradley, the AMPV program, and the now canceled Ground Combat Vehicle program, and tried to look for a way to do a common power architecture that would kind of be a la carte, where you could just choose the pieces that you would like and work around that in order to integrate a common architecture on the vehicle. So some of those requirements, we have 45 kilowatts of 28-volt power we're looking to produce. The total system power load, and this is kind of on a Bradley type vehicle, is 175 kilowatts. So that's what we're targeting today for the 600-volt distribution. We're trying to meet our silent watch requirement, which is engine off operation of 4 kilowatts for about 4 hours, and so we're planning on having low voltage batteries this time to do that, just based on where the lithium ion is at within the military. We also are going to have an import-export converter, which is kind of a vehicle-to-grid converter at 30 kilowatts. And the reason we chose 30 is that's the same size as a tactical quiet generator the Army has today. And so a vehicle could pull up and basically have a tactical quiet generator embedded on it and be able to power external, usually communication loads or medical loads. We're also planning to have bidirectional capability with both the 110 and 220 connections. We're looking to use the SAE J1772 electrical connector for importing and exporting high voltage DC power. There's a group working on trying to make that connection cyber secure. So although we're going to use the connector, it's going to be a little bit different from a communication standard in order to start exporting power. One of our main environmental requirements is we're targeting 105C liquid cooling for any box in the system that requires liquid cooling. We're going to implement this automated power management, power control strategy where you can dynamically turn loads on and off depending on your situation. And then lastly, we have, it's a publicly available spec, ATPD 2404, which is the Abrams and Bradley standards that they're trying to meet. It's based mostly off the MIL standard 810 and the EMI standards for that. So this is a quick, I know it's an eye chart, picture of where we're at in our electrical architecture development today. So I just kind of wanted to bring this up so if folks are interested in kind of how we're planning to implement, you can kind of see some of that there. I'll just speak to a couple things on this chart real quick, but knowing it's an eye chart, this is a publicly available briefing, so you can kind of get it and kind of look at it in your own time. But at the top in the center, there's this low voltage vehicle power manager. That's going to be the smarts for our system. It's going to tell us if the vehicle is too cold to turn on, and there's going to be some thermal relays in it, and it'll notify via lighting an LED to let the user know, hey, you need to do something to heat your vehicle up. It'll let you know by communicating with the battery monitoring system if it is too cold or too low of energy to start your vehicle, or kind of where you're at there. You can see that for the 45 kilowatts, there are 3 DC to DC converters, so we're looking at having 3 common 15 kilowatt DC to DC converters. We're going to have a high voltage air conditioning system with a high voltage coolant pump. We're also going to have an electric fan drive system, which will come off the generator controller, which is at the bottom left-hand corner. As far as the high voltage components go. Some of the other components that we're going to develop inside this battery box, kind of in the center, we're working on a battery isolator unit, which is a 500 amp bidirectional DC to DC converter to isolate the battery pairs, so that way during engine cranking we can still provide clean power to the auxiliary loads. And I believe that's all I'll talk to on this chart for now. So some of the features, at least what I'll call power management of this architecture, is some things that military vehicles can't really do today. So one of the things with NATO power, every vehicle the military has a NATO connector on it, which is this 28-volt standard connection. When using the NATO, it's usually directly connected to the batteries today. And so if you plug into a vehicle, you could discharge the vehicle's batteries, and there's nothing the vehicle can do to protect itself. So one of the things we're adding into our system is this idea of using a voltage comparison. So if the voltage on the external output is less than the energy storage, then that connection will remain open and no power will flow through. So that way you can't inadvertently discharge your vehicle batteries without turning the host vehicle on. And then likewise, if the voltage is greater, the vehicle will gladly accept, providing it's within the acceptable range, the 20-volt power to charge the batteries. And the system's kind of set up to where it'll automatically turn on the correct circuitry to charge the batteries off the NATO. Likewise, we're going to have this 3-phase AC inverter that I spoke of, and that's going to allow us to do some grid connection to intelligently charge and maybe even use the vehicle's batteries as some kind of stabilization to a microgrid to both charge and discharge the batteries. And so providing that there is power being provided to us, it will automatically charge the batteries, but in order for the vehicle to be able to provide the charge back, it'll require the vehicle being turned on. And then the coolant pump would operate as needed during charging for that. We're also going to have the 600-volt J7072 connection to be able to export high voltage power. Now, there's no, the vehicles that have been fielded so far today, they have no way of exporting this high voltage DC power. In the future, we want to use this DC power as maybe the basis as some of our microgrid connections. And so this is something that we're looking to put on the vehicle more as forward-looking. But until vehicles are actually fielded with 600 volts, there's going to be little use for this connection. Lastly, we're going to have an APU utility mode, which is a capability if the user would desire, after they park their vehicle for a long-term stowage, to keep your batteries from self-discharging. You can go into this APU utility mode where the vehicle will automatically turn on, wirelessly report status, and then turn back off just to keep the batteries topped off. And I wouldn't expect that that would happen very often or for very long, but it is a capability or an intelligence we're trying to build into the system. So kind of why standardize? Why is the military looking to standardize? So we believe that if we go to a common standard on both the 28 volt and the 600 volts, that'll be to the benefit of pretty much all the parties. So we believe that component designers would know the requirements they need to build to. Like right now, today, if you'd go ask the OEMs, each one would give you a different voltage to target for the high voltage side. And so we kind of think that we could get more components or a lot more common synergies, between the development if we had a common high voltage DC bus that we're working towards. The military wouldn't be paying for separate designs every time it does a new vehicle, and so to me that's a huge benefit. And then lastly, the people doing the system integration, they would kind of have like a menu of components to choose from. So today when I do a 28 volt system design, I can just pull up all the components that meet MIL standard 1275, and I can kind of work within that set in order to design my electrical system. So speaking of 1275, we've recently did an update to that from Rev D to Rev E. One of the things we changed about that specification is we made it so that it was a load-specific standard. And so we removed the constraints of a complete system design from MIL standard 1275, and we tried to guarantee that at the load you would have between 20 and 33 volts, including ripple, at the load. And so what we're hoping to see from this is that that's a little bit cleaner of a power standard. It used to be on MIL standard 1275, you had to go down to 6 volts, and then in some cases, if you considered yourself clean, it would still have to go down to 16 volts. So in most of the military loads we have don't operate below 18 to 19 volts. And so we were hoping that that would provide a little more stability, reduce costs in the power supplies that people were designing for their loads and that kind of thing. And then likewise, we're going to apply that. We currently have MilPerf 600A, which is a PEO GCS 600 volt standard. The reason why it's PEO GCS at this time is because they were the first that were planning to field a 600 volt system, but since then they've transitioned that specification to TARDEC. We're going to modify it a little bit this summer and then re-release it as hopefully a MIL standard. But essentially the requirements for that MIL standard is 565 to 635 volts, and that's kind of what we're targeting for when I say 600 volts. That's kind of the range, and there's a little bit of a ripple allowed within that range where we expect loads to operate through. So those are some of the requirements you'll see on our 600 volt side. So kind of the products and outputs of my efforts and kind of where we're at. And so we're going to have, the government plans to write all the software and own all of the interfaces on this architecture. We're not planning to design in-house any of the power electronics. And so we're going to develop performance requirements of what we'd like every box or component within the architecture to do and the connectors they're going to have. But outside of that, we don't plan on designing internally any of the components in the box. So we're going to have all these performance specifications and interface control documents for every piece of hardware within this architecture. Some of our goal on that, as far as having the first draft of those documents, is sometime this summer, because we'd like to start purchasing the remainder of our components around that time. We're going to update the 600 volt specification, like I said. We've already updated the 20 volt MIL standard 1275, so that one's likely going to stay as is. And then we're going to have silicon carbide power electronics available for demonstration. We're hoping around the August of 2015 timeframe, where I can show several silicon carbide products. Some silicon carbide effort I didn't mention. We have an effort with SAIC currently to develop a 175 kilowatt generator inverter. It's roughly going to be about the size of a large shoebox, and that's leaps and bounds ahead in terms of a power density standpoint from what we have available today. But I believe that product is scheduled to be delivered to us in about 18 months. Is kind of where we're at in the development cycle for that. We're also looking to have this vehicle control software that I mentioned that does all the power management and power control for the anti-idling, along with being able to have programmable load states where I can have like George's favorite load state and it'll turn on and off the correct electrical loads. It'll also have kind of a smart shutdown where loads won't turn off until they're ready to be turned off. And then we're hopefully going to have a host of components that if anyone would be interested in demoing what they have, we could connect them within our laboratory here at TARDAC and say, yes, this is compatible with MIL Standard 1275, or yes, it is compatible with our 600-volt architecture. So one of the things we want to do, we want to have as much industry involvement as possible with our design. And so when we did 1275, I basically sent every contact I had the updated specification to try to gain feedback and adjust our specification accordingly. We're planning to do the same thing with our preliminary design review materials for this architecture and for the 600-volt specification because we believe without industry buy-in, it's not really going to get us very far, even if the military decides to move forward with this. And so that's kind of where we're at. So we're looking to have that preliminary design review early June of this year. Hopefully we're still on track for that. And then having the final design review near the very end of 2014. Our goal, like I said, is we want to have this laboratory set up here at TARDAC and have everything demoed at what we call Technology Readiness Level 5, which means everything's connected in this laboratory environment and working by the end of 2015. One of the other neat things about this laboratory is we have our own EMI chamber, which will have the ability to liquid cool components and provide high voltage DC power and also a 28-volt DC power. And so we'll be able to do quite a bit of EMI testing on each of these components in this laboratory as well.
So this is the final presentation in the series on high voltage DC. We have had many guest speakers, as are identified here, from Hewlett-Packard through Emerson and the Fraunhofer Institute in Germany. So a lot of information. Seminars 1 through 7 are recorded and online on the vicorpower.com website. And within probably 10 days, we hope to have George's presentation on the Army 600-volt spec also recorded and available.